All right, let's dive right into this explainer. If you've ever stopped to wonder exactly how platforms like YouTube Shorts or Instagram Reels manage to deliver an endless, perfectly tailored feed of videos in literal milliseconds, well, you are in the right place. Today, we're going to totally reverse engineer the incredibly complex machinery that keeps us all constantly swiping, mapping out the complete system architecture from the absolute ground up. Now, to really understand this architecture, we have to respect the sheer scale of the thing. I mean, the engineering stakes here are absolutely massive. We're talking about processing 500 million daily uploads and serving up 50 billion low-latency views a day without the system breaking a sweat. It's an infrastructure challenge where even the tiniest bottleneck can literally result in millions of users just closing the app. So here's how we're going to unpack this. First, we'll look at the short-form scale challenge. Then, the ingestion and processing pipeline. Next, managing metadata and storage. Fourth is the recommendation engine, followed by global delivery via CDN. And finally, we'll wrap up with scaling for billions of views. Okay, let's jump straight into part one, the short-form scale challenge. Unlike traditional, long-form web browsing, short-form swiping is a whole different beast. It requires sub-100 millisecond latency per video load. Why? Because any delay, and I mean any delay, instantly kills user retention. We're essentially building an infinite scroll feed driven by an algorithm, so it needs to be highly available, it has to survive massive, sudden viral spikes, and it needs 100% data durability, meaning once a creator hits upload, that video is never ever lost to a server crash. Moving right along to part two, the ingestion and processing pipeline. So what actually happens when a creator hits upload? Well, the video doesn't just magically drop into a database. First, it flows through an API gateway for security and rate limiting. Then, it goes into a temporary buffer, think something like an AWS S3 multi-part upload, just for validation. Only after all that does it hit a message queue. This queue routes the file to these really heavy-duty transcoding services, where it gets converted into a bunch of different resolutions using FFmpeg, which is this incredibly powerful industry-standard tool for manipulating video. And then, finally, it rests in permanent storage. Now, looking at that pipeline, you might be wondering, why don't we just process this video synchronously, like the very second the user clicks upload? Why even bother with the message queue at all? Well, it's because video processing is intensely compute heavy. A short video might take 30 seconds to transcode across all those different formats. If we did this synchronously, the user would just be staring at that dreaded spinning loading wheel of death the entire time. By using an async message queue, like Apache Kafka, for example, we decouple the services. The user gets an instant upload successful confirmation, while all the heavy lifting, like the transcoding and the parallel machine learning moderation to make sure the content is safe, happens securely in the background. Plus, the queue absorbs any viral bursts of upload so our backend workers don't get completely overwhelmed. All right, let's move to part three, managing metadata and storage. This brings us to an absolutely crucial golden system design rule. You must separate your metadata from your blobs. Massive, immutable video files have to be kept in permanent object storage, totally isolated from the fast querying databases that handle our metadata. If you try mixing heavy video blobs with lightweight text like titles and view counts, trust me, it's a complete disaster for both performance and cost. Because different types of data behave differently, we actually have to use specific databases for specific jobs. For strict video metadata that needs strong consistency, we use relational databases like Postgres. For the social graph, tracking who follows who, we use graph databases like Neo4j to avoid the really slow, compute-heavy cross-referencing of traditional databases. And for all those likes, views, and comments you see updating live, we rely on blazing fast wide-column stores like ScyllaDB or Cassandra to handle those millions of real-time engagement writes per second. But wait, think about this. If we queried the database every single time a feed displayed a view count, we would effectively DDoS our own system. We'd accidentally crash our servers with our own traffic. So, to prevent this, we utilize Redis for sub-millisecond in-memory reads backed by what's called a write-behind caching pattern. Basically, when you like a video, it writes to Redis instantly so you get that fast UI feedback. Then it publishes an async event to Kafka, which eventually writes it to a persistent database to guarantee the data is safe. Let's shift gears to part four, the recommendation engine. Filtering billions of videos for a single user in just milliseconds requires a massive processing funnel. It happens in 3 steps. First, candidate generation uses collaborative and content filters. This essentially looks at what present.
Second, deep learning ranking scores those candidates. And finally, re-ranking shuffles the top choices. This is super important because it injects freshness, enforces diversity, and prevents those really boring echo chambers.
Now, the machine learning inference surfaces driving that ranking stage, they don't just optimize for cheap, immediate clickbait. No, they analyze hundreds of features in real time. We're talking user history, session markers like the time of day, and video embeddings, which are basically mathematical summaries of what's actually in the video. The ultimate goal here is to predict an engagement probability that maximizes long-term watch time and overall user satisfaction. Which leads us right into part 5, global delivery via CDN. Imagine trying to deliver a video hosted in Los Angeles to a user in Tokyo directly from the origin server. It creates intolerable lag. We're talking over 150 milliseconds just from the laws of physics alone. To beat physics, we absolutely must cache the most viral content at hundreds of global CDN edge locations. By placing the video physically closer to the user, we achieve sub-10 millisecond latency. Plus, we handle up to 90% of the platform's traffic without ever even touching our main servers. But, as we all know, mobile networks are famously spotty. To ensure smooth playback even when your signal drops, we use adaptive bitrate streaming. The video player in the app is constantly monitoring your network connection. If your connection gets weak, it seamlessly swaps the video to a lower resolution file. Remember those 480p or 360p versions we generated way back in the ingestion pipeline? Yeah, it swaps to those so the video never actually stops to buffer. So the real secret to creating that magical instant swiping experience is prefetching. We literally cannot wait for you to swipe before we start downloading the next video. Instead, based on algorithmic probabilities, we predictively load the next 2 recommended videos directly into your phone's memory in the background. When you finally flick your thumb, the transition feels completely instantaneous because the data was already sitting right there waiting for you. Finally, let's wrap up with part 6, scaling for billions of views. To survive unexpected failures at this insane scale, we can't just rely on making single servers bigger. We have to scale horizontally across thousands of commodity machines. Every microservice has to be deeply monitored by distributed tracing tools, like Jaeger, to pinpoint exact bottlenecks. And perhaps the coolest part, we constantly stress the system using chaos engineering. This literally means intentionally breaking databases and unplugging networks in production. I know, it sounds absolutely terrifying, but it's the only way to prove true automated resilience. So, to summarize this entire architecture, if you're ever designing for billions of users, always remember these golden rules. Rigorously separate your metadata from your massive blobs. Decouple your heavy compute services using message queues. Aggressively cache at literally every single layer from the edge inwards. Always use specialized databases tailored for specific data workloads instead of a one-size-fits-all approach. And lastly, process your heavy compute asynchronously. Now that you've totally mastered the complex machinery behind a 50 billion view short-form video platform, I want you to ask yourself something. How would you twist these exact same design principles to build the real-time location matching of Uber? Or what about the globally encrypted messaging of WhatsApp? What components would you change and what stays exactly the same? Think about it, and we will catch you in the next explainer.